The basic idea of this talk is quite simple. Anybody who decides to hire an astronomer for a year deserves to see pretty pictures. And so I started with that premise of taking the most beautiful images in planetary sciences that I could get my hands on, one or two of which I can say I had something to do with, most of which are images taken by friends of mine. And I'm putting them together in a story that describes a little bit of what's going on in the solar system. As I present the pictures and tell the story, I want you to participate. I want you to ask yourself, do you find these images beautiful? Do you find them beautiful more or less when you hear my explanation of what they're about? Does it add or does it detract? And the bigger question is, why are they beautiful? What is it about them to you that makes them beautiful? Professor Rocasalvo has been sharing her book in progress on the nature of beauty, which, if nothing else, has shown me just how little I understand about beauty and how much there is to be said about it. So I'm not coming here with any answers to these questions myself. I have ideas, but I don't by any means claim that my ideas are correct. And being a good Jesuit, I've got a counterexample to every idea that I've got. I start with this image, which was taken by a friend of mine, a fellow Jesuit, a fellow named Manny Carrera. Dr. Carrera is originally a physicist who worked in cosmic rays, but he's also an amateur astronomer and an amateur photographer. He taught many years at John Carroll University in Cleveland and at the Jesuit University in Madrid, and would spend his time in half in each place. He's Spanish originally. He took this picture at sunrise from the Papal Palace where we have our observatory in Castel Gandolfo. And this is looking across to a rock called Rocca Priora, and you notice the castle there. We are located south of Rome. If you are marching up towards Rome with your army, this is the first line of defense of the Roman defenses in the Alban Hills. This would be a fortress that you would have to encounter. And the nature of sunrises being what they are, twice a year the sun will rise exactly behind the castle. What I find fascinating myself in terms of just the image and why it's beautiful, it's more powerful, this version, than the picture he took a few minutes earlier, which has the castle actually in the sun itself. The sun, the source of light, is a powerful source of beauty. And this next picture was also taken from Castel Gandolfo. And it also is a picture of the sun, seen through a telescope with a thick filter. This picture was taken in 2004 on, I believe the date was July the 8th, if I remember that date. This was a date when Venus, this planet, a planet the same size as the Earth, passed between the sun and the Earth. It's called a transit of Venus. Transits of Venus occur twice every 120 years. Essentially, you'll get a transit 8 years later, you'll get another transit, and then it's another 112 years before the next set of transits. 2004 was the first one we'd had since the 1880s, and the 1880s was the first we'd had since the 1760s. Why is this important? It's important for a number of reasons. Part of it is simply the magnificence of seeing the granulation of the sun compared to the shadow of the planet. This image, both of these images, were taken by an amateur astronomer who was at Castel Gandolfo with a group from Sky and Telescope magazine. And he had essentially an advanced amateur's telescope and camera and set of filters, and managed to come up with images which 20 years ago even a professional could not have done. That's what's happened to the technology. The story behind the transits is a fascinating one. How do we know how big the solar system is? One way to guess how far the distance is from the Earth to the sun, besides looking it up in a book, we'll put it in the book, If you look at the sun in the sky, it's half a degree across. If you held up a dime at arm's length, the dime is bigger than the sun. It's only a half a degree across. If you knew how big the sun was in terms of miles, and you knew it was half a degree, then you could use trigonometry to work out how many kilometers or how many miles it is to the sun. But how do you actually know how big the sun is? Again, you need triangles. When Venus crosses the sun, if you have people on two opposite sides of the Earth, both watching Venus cross, because of their different distances, they will see Venus cutting across the disk of the sun at slightly different positions. And you can time how long it takes. It's a matter of hours. It's about 8 hours. Time it to the second and work out where on the circle of the sun that chord is. Work out how far apart the chord is from people on one side of the Earth versus people on the other side of the Earth. If you know the distance between the people, and you know the distance between the chords, and you know the fractional distance of the Venus, which acts as the fulcrum to make this whole triangular bit work, you can calculate the size of the sun, and from that, the size of the solar system. This was worked out by Edmund Halley, Halley's comet fame. But he also knew about this 120-year business, and he realized he would not live to see the next one. He worked it out and left it for posterity, and it was left to a group of mostly French scientists to organize the international effort to work out the size of the solar system. Unfortunately, the first transit that was visible with telescopes that people were ready for occurred in 1761, which is in the middle of the 7 Years' War, what we call in America the French and Indian War. Because it was wartime, and the French and the English were fighting each other, there were all sorts of adventures of people attempting to make these discoveries, to make these observations, and getting captured by one group or the other. There was a French scientist who wanted to go to the French-held India, but by the time he got there, it was no longer French-held, it was English-held. His captain refused to land. He missed the first transit. He stayed in India for 8 years to wait for the next transit. He was clouded out that day. When he finally got back to France, he found out that the letter he'd written home saying, "I'm going to be late for dinner," was lost. They thought he was lost with it. His wife had remarried. His job had been given. The importance to the Americas, among other things, was that in order to make this observation, you needed an astronomer and a surveyor. You needed the astronomer to observe the Venus. You needed a surveyor to know exactly where you were so you could measure out how far you were from the fellow back home. Well, the Astronomer Royal of England, Flamsteed, sent his number 2, was a fellow named Charles Mason, to go off to the South Seas. The surveyor he took with him was Jeremiah Dixon. And they stopped in the Americas on the way home to do a little bit of surveying. And that's where the Mason-Dixon line comes from. The one other connection was that for the second transit, the Astronomer Royal hired a British ship. The war was over. And then at the last moment, the British Navy said, "You can have our ship, but we want our own captain," a young lieutenant by the name of Cook. And that's how the entire tradition of Navy expeditions run by James Cook or James Kirk, depending on whether it's Starfleet or the Endeavour, in the practice of measuring the Earth. The idea that there's so much history tied up into an image like this, which also shows you solar flares the size of a planet, which shows you the atmosphere of the sun. I'm blanking on the name of the fellow who did the photography. I'm so embarrassed. It's the trouble with not having it written. I only mentioned that he was a Dershowitz, something like that. It's a good Jewish name. No, it's not Helen. No, he's a professional, Ron something. I mentioned it because after the event, his father came, we went out to dinner, and it was a hot summer day, he was sitting in the restaurant, and I noticed that his elderly Jewish father has a tattoo on his arm of a number. And it reminds you again, I'm in Castel Gandolfo, an area that was in the heart of the fighting during World War II. in gardens that served as a refuge for 12,000 refugees, many of them Jewish, taken care of by astronomers who were Jesuits, who were Germans. There's history tied up in all of these things. There's history in a lot of what I do. This is a rock that is part of a meteorite collection that was at the Vatican Observatory when I arrived. I have an expertise in meteorites. The Vatican had a collection that needed curating. The fellow who assigned me to the observatory did not know either of those facts. This particular meteorite, Krasnojarsk, I remember the name of the meteorite, I can't remember the name of the person, is an interesting one because it's bits of metal with these green crystals embedded in it. Both the metal and the green olivine crystals, the same material that you get on the green beaches in Hawaii, have been molten and crystallized, and the crystals are quite large. This entire piece, this is about, in fact, that big, so it's kind of blown up. But they're large crystals. Both have been melted. Both have been crystallized. How is it possible to have low-density olivine and high-density metal melted and crystallized without them separating, with the lighter stuff floating to the top? It happens if this occurred in the center of an asteroid that doesn't have much gravity, so that it doesn't know where a top is. We have in our meteorite collections pieces of planets that were in the asteroid belt that do not exist anymore. We think at least 50 different planetary cores, 50 different small asteroids, dwarf planets, that were big enough to melt, differentiate, make a core, make a crust. We see in the asteroid belt today one such differentiated dwarf planet. All but one were destroyed by something that happened 4.5 billion years ago at the formation of the solar system. And this meteorite is evidence of bodies that do not exist anymore. I love meteorites. Meteorites are pieces of outer space. My fellow astronomers think that they're studying stars and planets and galaxies. They're not studying stars and planets and galaxies. The only thing they can study are photons. The only thing they get to study is light from stars and planets and galaxies. Whatever light they can capture. I get to see the real thing. I get to see the actual pieces. This is a thin section of a meteorite, an ordinary chondrite, one of the most ordinary kinds of meteorites you can get. It's actually about a few millimeters across here. You take a rock, you slice it very thin, you make a slice that's about 10 microns, thinner than a human hair, glue it onto a piece of glass, shine a light through it, and you don't see this. But before you shine the light through, you put it through a polarizer, polarized this way. Then you have the meteorite. Then you have another polarizer, polarized crosswise to it. If you have light polarized this way, then a filter crosswise to it should not pass any light. But if you put something in between, in some strange and wonderful way, that I could wave my arms and try to explain it, I would be wrong, but in fact, a way that involves the quantum uncertainty nature of light. The crystals here allow light of a certain color, depending on how I've twisted this slide, to come through both polarizing filters. But only light of a certain color comes through. And if I took and rotated the stage that the thin section is on, you would see, like a psychedelic light show, the crystals changing color from red to green to yellow to blue. The colors and the rate at which they change color and the point at which some crystals go black. By measuring the angle where they go black, you can actually work out the chemical composition of the crystals, the iron content of the olivines and pyroxenes, which is a way of classifying meteorites. There's a lot of information, scientific, you can get out of this. But it's also difficult to do science when all you're doing is looking through a microscope going, wow. And, oh yeah, that's right, it's just actually getting a number out of this. You notice the round bit there, and there are actually little fragments of round bits everywhere. Meteorites are very strange. Meteorites were not part of a planet that blew up, even those dwarf planets. These weren't. These were never melted. You can tell from the chemistry that large chunks of the dust in there never saw a temperature more than a few hundred degrees. But the round bits were melted. The round bits looked like bits of dust that were flash melted, formed themselves into a droplet, and then froze over a period of about 8 hours. If you had told me that they froze instantaneously, I could explain that. If you told me that they took thousands of years to freeze, I could explain that. 8 hours is very hard to explain. But that's the only way you can get the ratio of the trace elements from the outside to the inside, the size of the crystals, a number of other tricks that you use to work out the actual cooling time. There are more theories for how these little droplets were actually melted, where they were melted, when they were melted. More theories than there are theorists, because everybody's come up with at least 2 theories. We don't know for sure, or rather, everybody knows for sure, they just don't agree with each other. But it's telling us, again, something about what was going on in the earliest days of the solar system. The thing that I'm fascinated by is that you have the dust and these round balls packed together so densely that, in fact, there is no pore space, that they are completely compressed. That happened in the absence of flowing water, or high temperatures, or high pressures, the things that normally make sand into rock on Earth. How did that happen? The only thing I can assume happened is that there were some kind of collisions that ran shockwaves through that melded these bits of grain close to each other. The exact way that it happened is still a mystery. A lot of my research, the work I've been doing at the Natural History Museum here in New York City, has been measuring, trying to figure out, can I find any pore space in this material. That's half of my work, looking at rocks. The other half is, because I work at the Vatican Observatory, and the Vatican Observatory has a telescope, I figure, why not use the telescope? This is an image that a bunch of colleagues and I took a couple of years ago, and what we're really interested in is this dot down there. This ugly galaxy just gets in the way. Terrible things about galaxies. So yeah, there's 100 billion stars there, and who knows how many civilizations, and who knows how many planetary scientists trying to look back at us. This is a close-up of what we looked at. And it's not a multicolored streak, it's that we took the picture first through a red filter, then a green filter, then a blue filter, and glued the 3 pictures together to make a nice color picture here, but the object in question moved. This object, unlike everything else in the picture, which is either a star thousands of light years away or galaxies millions of light years away, this is a mere 50 astronomical units away. Actually, that one there is about 10 astronomical. It's only about as far out as Neptune. It's a small body which is orbiting from out beyond Neptune, out where Pluto is, out where the rest of the Kuiper Belt is, coming in towards the inner solar system, which in some future day will probably break up and become a comet or a family of comets, in future day being thousands to millions of years from now. We're merely trying to figure out what is its color. What can the color tell us about what it's made out of? Because it's from so far out, we're pretty sure that it's made up of ices. And bodies made of ice have been something that I've worked on for a long time. The moons of Jupiter are mostly bodies made of ice. This is one that is not a body made of ice. It's mostly rock. This is the moon Io, closest moon to Jupiter, imaged about a month ago by a spacecraft that went past Jupiter on its way to Pluto. And you can see the phenomenal volcano there. You can also see that even though this is the side that's in the sun, this side is well lit because Jupiter's over there, and Jupiter light is shining back on it. There's a story behind this, of course. In 1979, I was a first-year postdoc, there were a couple of theorists who had worked out the nature of Io orbiting around Jupiter, but being pulled on in a regular way by the other moons, Europa, Ganymede, Callisto. And this tug of war between Jupiter and the other moons they realized would cause the body to flex ever so slightly. But you know, if you work things, whether it's dough or whatever, it gets hot. They calculated how much energy there was, and they said, there's enough energy that you could melt, not too far below the surface. In fact, they predicted that there would be volcanoes, active volcanoes, in Io. The paper came out 1 week before the first images of Io from a spacecraft were finally taken, the Voyager spacecraft. Spacecraft flies by Jupiter, takes a bunch of pictures. They're still, trying to color balance them and work things out right. One of the engineers is using some of the images simply for navigation. They know where the camera was pointed, they know where Io was supposed to be, find out where it actually was in the picture, we can work back to where the spacecraft actually is. And they had a computer program that would take the image, fit a circle, find the center, tell you what pixel that was, and the computer program came back and said, it doesn't work. What do you mean it doesn't work? Well, I can't fit a circle. You mean it's big, right here. And the program says, well, yeah, there's a big thing, but then there's this lump. They looked at it and said, is that another moon we didn't know about? And the engineers finally realized it was one of those volcanoes, but far more spectacular than anyone would have thought. So after the scientists had predicted, it was actually the engineers who discovered the volcanoes. Wonderful happenstance of a story. I had one of the original Discovery pictures like this. I would tell this story when I was in the Peace Corps in Kenya. I remember I gave a couple of talks up in E10, which is an area just above Eldoret, where all the great runners come from. And one of my fellow Peace Corps volunteers was teaching at a girls' school there. So I was telling, giving the slideshow, telling the story, all of that. And I said, so Linda Morabito, the engineer, was working at that. And when she realized, and all the kids looked at me, she? And all of these girls at the girls' school were so excited that a she had made this discovery. And so, there's, triumph for feminism and all of that. Great. Next night, I'm giving the same talk up the road at the boys' school. Get to the same point, wondering what kind of reaction. One of the students came up to me afterwards, very seriously, dead serious, and he said, sir, he said, I love it, they call me sir. Sir, you should not have let that woman make that discovery. One of the reasons I was interested in the moons of Jupiter and their iciness is because my original master's thesis was trying to predict whether moons that were made of ice would actually melt. And the answer was an unequivocal maybe. Depends on all sorts of things, including a lot of things that I didn't even know about, because I was 22 years old. Imagine then sort of my surprise and delight when last year the Cassini probe to Saturn had this image of Enceladus and showed streams of volcanoes, but this time not sulfur, like the ones that are spewing off of Io, but water. Liquid water streaming out the South Pole. It got me wondering, this is a picture now taken from behind Enceladus, looking towards the sun, so you can really see the plumes. This is it's only a couple hundred kilometers across, a couple hundred miles. It's a small, low gravity, must be completely covered with ice and snow. What a great place to go skiing. But imagine now you've got your ski resort located near the South Pole. You could be anywhere about 40 degrees south, and you will see these plumes off in the distance every night. Nights occurring about once a week, our time. And you will see sunlight coming through these driplets, almost certainly creating a rainbow pattern. Imagine walking out into the dark with all of the stars above you. Maybe if you're lucky, with Saturn behind you. Looking and seeing this array of crystals reflecting light towards you. Somebody, someday, is going to make a heck of a photograph. But that reminds me, of course, of Saturn itself. Saturn is one of the most beautiful objects. You can see this almost that good in a little telescope from the roof of a building right here on campus. It's so bright that even the city lights don't kill it. Saturn has little moons, that's one of the little moons. But Saturn mostly has these rings. This is a great picture. This was a Cassini picture. You can tell it's not taken from Earth because you can see the shadow here. The sun is off in that direction. And the Earth and the sun are going to be roughly the same place because Saturn is so far away. But the Cassini spacecraft also went behind Saturn and gave us this image. From this direction, you can see not only the atmosphere of Saturn, which acts like a giant lens focusing light back down onto the spacecraft. You can see all of the dust in the rings. Big lumps of dust reflect light back at you. Small grains of dust, grains the size of the wavelength of light, scatter the light forward. And so here we can see not only the dust in the rings, the thin E ring, but also the larger rings. This ring in particular is caused by the water spewing out of Enceladus, which leaves a ring of ice crystals around Saturn. Now, even though this is being filmed, I'm going to try to do something else here. I'm going to turn down the lights, very dark just for this one. Can you see right there a little dot of light? I'm told, I can't confirm it, I'm told that that's planet Earth. The spacecraft is here, the sun is off in that direction, and the Earth is off to the side. Saturn has a moon called Titan, which is about the size of planet Mercury. It's a very large place. And Titan has an atmosphere. The Cassini spacecraft sent a probe with a parachute that went through the atmosphere and took images. Now, the temperature there is about 80 degrees above absolute zero. It's 200 and some degrees below zero Fahrenheit. It's cold. But you see on the surface what look like river channels and flat areas and clouds. What substance at that temperature could be liquid? The answer is not water. The crust is probably made of water. The liquid that's falling out of the air is mostly nitrogen, the same as the air here on Earth. But the stuff making the clouds and forming droplets and falling on the surface is methane, better known to us as natural gas. There are rivers of natural gas flowing into oceans of natural gas. We're trying to tell Dick Cheney that, so we'll go and, invade that place so we can get some of their. It's spectacular that looking down from above, you can see a shoreline, an unexplored ocean, a place where you can have adventures. But we also followed the lander until it hit right at the center there. It gave us 1 or 2 pictures from the surface. Now, these look like boulders. In fact, they're only a couple of inches across. They're very close to the camera. The surface is mostly water. Even the boulders are water. They're just frozen water, very hard, rock hard. But then, if you raise rock to a high enough temperature, it turns liquid, becomes a lava. The curious thing is, when the lander hit, it settled down, and there was a little accelerometer so we could tell how fast it was going when it hit. And it hit, and it stayed for a minute, and then settled down a little bit more, as if there was a hard crust and a little bit of soft stuff underneath. It was described by one fellow as creme brulee. So, it's a surface which is a little squishy. We thought this was going to be an ocean. In fact, it was designed to float if it was an ocean. You can see it's not an ocean. It's got rocky surface. Conceivably, there could have been liquid there in the past. There are other regions that we've seen with radar on the surface that are so flat, people have been arguing they really are lakes, if not oceans. It's again a completely unexplored and different world. Water, liquid, organic materials all bring to mind the thought of life. Going back to my icy moons, this is an image of the surface of Europa, the next moon out. A moon which has got a rocky core but a thin 100-kilometer or so icy shell. And we've got reason to believe that there is actually liquid water at the bottom of that shell. That water appears to have dissolved salts, which makes it a conductor which distorts Jupiter's magnetic field the way that a liquid would. When you look at the surface, it's all frozen. But it's frozen with regions that look like pieces of ice that have broken apart, moved about, and then been refrozen into the surface, looking very much like there was, at least at some time, liquid that may have come very close to the surface. The idea of these pieces moving around is evidence of ice floating on top of a liquid. When you look to the North Pole of Mars, this is what you see. Very similar. Is it the same thing? Is there liquid water, or was there liquid water on Mars at some time? The evidence is strong that Mars once was much wetter and much warmer. There's clearly no water on the surface today, but we have rovers that have been running around the surface of Mars for the last 3 years, constantly finding evidence that Mars could have had life. No evidence that Mars actually does have life. One of the strongest bits of evidence we have about the nature of Mars is comparing what the orbiters see, what the rovers see, with meteorites. Going back to my meteorite collection. Meteorites that have traveled from Mars back to the Earth. In fact, we even see meteorites on the surface of Mars. Meteorites hit Mars just as much as they hit the Earth. Where do you think these big craters came from? Meteorites that come from Mars don't look like your typical meteorite. A typical meteorite, most people would have a hard time recognizing as not just another Earth rock, unless you were trained. But if it's a Martian rock, it's a basalt. It doesn't look all that different from a terrestrial rock. The place you have to go to find rocks that are Martian rocks are places where you don't find rocks at all. Dry deserts or Antarctica. More ice on top of water. A very familiar scene. This is one picture I took myself. Out the front of a C-130 cargo plane, traveling from Christchurch, New Zealand to McMurdo Base in Antarctica. In 1996, I was part of an expedition of 6 people. Every year, 8 to 10 people are sent to Antarctica to look for meteorites. Meteorites are real easy to see. Meteorites are black, Antarctica's white. Anything that's not white, you pick up. It's also useful because the meteorites stay frozen. A meteorite that hits around here in Fordham, not only would you not recognize it, but the next time it rains, the water gets into it, it starts to rust, it falls apart. Another advantage is that the meteorites that fall in Antarctica are carried by the ice to regions where the ice suddenly is blocked by a mountain, evaporates away, and the meteorites are left behind. So there's a conveyor belt that collects meteorites from all over the continent and strings them along to certain regions. 1996, during our training, I took this image. If you're into cameras, the camera used here was a $3 throwaway Kodak panoramic camera that I kept in my pocket. This picture was taken looking due south at midnight. In the South Pole, then the sun should be to the north. but we're there in the land of the midnight sun. Looking due south, I'm looking into the wind. I'm downwind of the tents. What the heck was I doing up at midnight? Well, if I had taken a picture looking straight down, you would have seen a little yellow splotch where I was standing, which wouldn't have lasted long thanks to the ultraviolet light. The rule was you left your little splotches downwind, you took your drinking water upwind.
Oh.
But it's a remarkable picture of just reminding you this remote and incredibly beautiful region here on planet Earth. Yeah, we got 400 meteorites. Yes, we got a piece of the moon. Yes, we got some other very exciting rocks. To me, the thrill was, it was as close as I will ever get to being a spaceman on another planet. Yeah, that's me. It had that combination of being incredibly remote, yet never alone. I was always with other members of my team. Being in a place that was utterly alien, and yet felt like home. There were so many things different from what I was used to. The sun was in the wrong part of the sky. The moon was going in directions, and I like to orient myself compared to where the things in the sky are. I'm an astronomer. Things in the sky look different there. I'm an astronomer. The two things I know is you go someplace where it's dark and you look up. So if you're going someplace where it never gets dark, and I spent the entire time looking down. And yet, at the same time, as alien as it was incredibly beautiful. I have never seen such a beautiful place. The air was so clear and so pristine to breathe. The other thing, there's just a wonderful story that the fellow who runs the group, who is my tent mate, Ralph Harvey, tells. He says, he was showing these pictures once back in Cleveland, Ohio, and a little old lady in the audience goes up and she goes, "Young man," she says, "you've been to heaven." He's going, "What do you mean?" She says, "I had a dream. I had a dream about heaven, and it looked like that." And Ralph is very, very hard-nosed and down to earth, and not at all given to flights of fancy. And he said, all I could do was agree with her. It's a remarkable place. It's not the only remarkable place. It's not the only remarkable place where there have been people. Buzz Aldrin, Apollo 11, a picture that is phenomenally familiar to those of my generation, and yet I can never get enough of it, just to look at it. My last picture in the set, since I started with the sunrise and ending with the sunset, it's a sunset taken by the Opportunity rover on Mars. To me, the power of this image is that I can picture myself there, just as I can picture myself on Mars, on the moon, in Antarctica. I said I was going to show you a series of pictures and talk about beauty. I'm going to give you 3 questions, and without answers. Did you find the pictures beautiful the way I did? Did the stories I told about the pictures add to the beauty? In what way? And to what degree is it necessary, or does it add to have a human context to the beauty? My own reaction is the most beautiful pictures are the ones where I can picture myself there. Like here, where up here on the stage I can feel like I'm walking on Mars. Images where I can actually see the sky up, the ground down, a place where I could walk. The sunrise image, the very first one, Would that have been the same image without the castle? Without the evidence of human beings? The midnight sun in Antarctica, would that have been the same image without the tents? Is that a necessary part? Is beauty partly inserting ourselves into the image? Or, as I said, I've given this talk once before in Lincoln Center, someone came right back and said the most beautiful image in the entire bunch was the thin section of the meteorite. There's no way you could put yourself into that. I leave these as questions for you, and I thank you for coming and sharing some of the beauty where we find ourselves in the solar system. Thanks.
And Brother Guy has graciously agreed to take some questions.
Or comments. I'm interested to hear what your reaction. And these are very familiar pictures to me. If they're not to you, I'd like to know which ones you thought were great. And if you can put words to why. Yeah.
One of the remarkable things, I think, is how the human being completes nature, because it's all unconscious. I can't tell its own story. So the human being fulfills nature there by bringing this up and telling this story. So it needs us as well as we need to be completed by the people. And that no one else can tell its story. So it's waiting for us to bring it into the light of consciousness.
Even to the point of having to make the thin section and make the filters so we can see the colors there. Would not have been seen before. Yes.
Have your studies made you more religious?
No. I'm reminded of an interview I had where fortunately the reporter showed me the quote before they published it. And they asked me sort of, you know, is science the reason you believe in God? And the point I was trying to make is I believe in God for reasons that are faith reasons, and the science complements it. The science makes it richer and deeper. What I actually said was, I don't believe in God because of my science, I believe in God for other reasons. When it came in black and white, it was, Brother Consolmagno of the Vatican says, I don't believe in God because of my science. What I do find is that the God who I've experienced in my prayer, and the God who I experience in Scripture, and the God that I've heard all these stories about all my life, appears to be the same God I find in nature. That I see the same personality over and over again, the same sense of humor, if you will, the same mystery, but always a hint that allows you to join in the mystery. It's always an invitation to complete the picture. And I find that in interacting with human beings, I find that in God trying to straighten out my own crazinesses, I find that in trying to understand. And there's also the same wonderful sense of joy. C.S. Lewis wrote this book, Surprised by Joy, which was a great description of when the transcendent touches your life. And all of us have had these moments. And that's the same, very same familiar, wonderful joy when the data points are on the plot and I look at it and I go, oh my gosh, there's a pattern here. I've seen something I didn't know about before. So in that sense, it complements it. It gives me another way to experience God. You have a question?
I was wondering, could you go back to the slide of the thin slide?
Thin section,
yeah,
sure.
that you were talking about earlier. It was very interesting to me what you said, and then what Father Clark's comment was, because the whole time I was looking at that, and this may just mean that I'm here workshopping, but I was seeing a human shape.
Yes.
I was seeing a head, and I was seeing the various bodies, and almost an infant. And I was waiting for you to kind of point that out, and then I thought, oh no, I've done it again, I've seen something odd.
I've got dozens of thin section pictures. Why do you think I chose this one? And there again is part of the human involvement.
What is the scale we're looking at? How small is that?
John, you've looked at thin sections. I believe from there to there might be about 2 millimeters. A typical chondrule is about 0.5 millimeter across. So that would be the way I judge it. That's the kind of question a scientist would ask. What's your scale bar? What are you trying to pull on me? Let's see.
Recently I was reading something about dark matter or energy,
Mhm.
and how this is supposed to, if indeed there's so much of it out there, it's supposed to revolutionize the way we think about the universe. I'm wondering if you have any pictures or any slides that show any evidence of that, and what is your take on the existence of
There's
dark
two different
energy?
things, dark matter and dark energy.
Right.
It's very difficult to picture something you can't see. And I don't have any photograph of that any more than I have a photograph of God. And sometimes people refer to it as like God. The evidence for dark energy, which is the new stuff, the evidence for dark matter is pretty straightforward. You see stars and galaxies orbiting at a speed that's completely different from what you could explain by the law of gravity, and the star is visible. So you have to postulate that there is other material. And by looking at enough galaxies and enough orbits, you can actually plot out where this material should be. And so the material we can actually see makes up about 5% of the universe. The dark matter makes up about 30% of the universe. But the rate at which the universe appears to be expanding, and the geometry of the universe at large distances, and the fact that the expansion appears to be accelerating, is all consistent with general relativity and another kind of energy that we cannot otherwise see. We can only infer it exists, and all we know is that it must exist to make general relativity work. But maybe it's no more real than the epicycles were in the Ptolemaic theory of the solar system. Maybe what we have to do is throw out general relativity and come up with a new law of gravity. People are really reluctant to do that because general relativity has done a very nice job for us in the last 100 years. We don't know which it's going to be. 100 years from now, maybe 5 years from now, we'll be laughing at people who were suggesting this, one way or the other. It's great because it means we know something that we don't know, that we didn't know 5 years ago. And this was one of these great lectures my dad always gave me. He had long trips to high school. I was going to the Jesuit high school in the center of Detroit. And he's a great pontificator, as his fathers are. And he said, knowledge is like a circle. The more you know, the bigger the circle. The circumference of the circle is the part that you know you don't know, because that's the boundary between what you know and what you don't know. The bigger the circle gets, the bigger the circumference. And so if you see somebody who thinks they know everything, that's because their circle is very small. Yeah.
When you say that the whole universe is expanding, do we know from what point can we do the geometry and know where the Big Bang was or where it's expanding from?
The standard astronomer answer is no, we can't. My contrarian answer is yes, we can, and it's everywhere. What we're saying about the universe expanding is that every place was at the center at time 0. Every place is the center. And therefore, from the point of view of wherever you are, every other point appears to be moving away from you. So we're all centers. It's not that there's a bunch of stars moving out into empty space. It's that space itself is getting bigger. And if you understand that, you don't understand, because it's harder than that. The observations are such, every time you've attempted to test it, it's passed the test better than you expected it would. And the fact that you can work backwards to a time zero is again deceptive, because that's time zero in our frame of reference, which may not be time zero in the frame of reference of the material that's going through it. Just as the universe can appear to have a finite dimension because we can't see beyond the point that's expanding away from us at the speed of light. It's not to say that there isn't material out there, just that we can never touch it. But there is no there in our frame of reference. And yet it might, how can we talk about things existing if we can never have their existence impinge on us? It's a wonderful question of philosophy. And yet the cosmologists are dealing with this all the time. I point out, just to throw another monkey wrench, the fellow who came up with this crazy idea was a guy named Georges Lemaitre, who is a priest and an MIT graduate, but not a Jesuit. He hated it because he was a Jesuit. So smart people, you can be smart without being a Jesuit. And he worked this all out in the 1920s. People, the other astronomers at the time, were so convinced he was just doing it as some way of creating a creation point, they made fun of his theory. And that's where the name Big Bang came from. It was a mocking term. But in fact, it's taken hold just as it's passed all the tests. And all the other theories proposed to counter it have failed their tests. Yeah.
Yeah, I don't know whether this is a scientific question or not. Is the Earth itself being continually created due to its dynamic nature? Or is, as the Earth is changing, it would be it's changing because of its dynamic nature?
That's a philosophical and a scientific question.
Okay.
Or theological.
Mm-hmm.
I think the theologians would say that the fact that existence exists
Mm-hmm.
is maintained by a constant act of creation. That God the Creator not only starts things out, but allows things to continue. That this is the substrate that underlies all of us. That's a theological argument.
Mm-hmm.
From the point of view of the scientist, the way we look at it, all the atoms are bits of either matter or energy which turns itself back into one or the other. That's been around since the beginning. There's only so much matter energy. The atoms in the Earth are still matter energy that goes back to the Big Bang. There are new atoms being added to us all the time as the meteorites hit. There are atoms that are being blown away as the top of the atmosphere slowly gets eroded by the solar wind. We're continually seeing the Earth change. It's being driven by volcanoes, which are being driven by radioactive elements, which are decaying and which will never get their energy back again. That energy comes out of stars that they were forming. So that the Earth in 5 million years will be a little bit different than it is today. In the Earth in 5 billion years will be a lot different than it is today. So it's not a place that will never change. Change is the one constant. Yes.
Why do you consider that image beautiful?
I would argue 3 things. The colors are pure and appealing. I think the human form, I think the fact that I can impose myself into it adds something to it. I would also argue, and this is difficult to explain in a short lecture, that knowing what I know about where the colors are coming from in terms of the quantum effect, this is a beautiful example and demonstration that quantum physics is correct, because classical physics cannot explain this. And I love that about it as well.
When you explain the truth of this image, that is to say, you're explaining the design, etc., the truth of it in itself, isn't that an aspect, an important aspect of its beauty? That it is revealing itself to the eye in its truth.
It is, but as I say, I have a dozen, hundreds of thin section images, And this I chose because it's the most beautiful. All of them reveal truths. But this one has a special beauty the others don't have. Because of its colors, because I can see the baby. And so I think all of that plays into it. But that's a good question.
Well, that's,
We're running short of time, it's 5 o'clock, I'll take one more.
I'm going to drag this right back to the kindergarten level. The first picture was my favorite. The creation of man was silhouetted, imperfect. The sun was too bright to look into. I don't find putting myself in there, but that middle ground where the two are trying to reach for one another and make an experiential connection, which for me is about as good as you can get, because you can't understand the whole, and our physical is flawed. But that middle ground where they're kind of reaching for one another, I find fascinating, and to me, that's why it's the most beautiful.
And I think we'll find, if we took a survey here, everybody would have their favorites. Because part of what makes it beautiful is what we're bringing to the picture. And yet, I think everybody in this room could see the beauty in all of the pictures. Maybe just not the same stories in the same way. Does the fact that I was telling these long, boring stories about the history of these pictures, does that add to the beauty? Did that add to the experience?
Yes.
Okay. And that's telling you something. Thanks a whole lot for coming.